So we saw that the limitations of the event horizons, and then we're looking for quasi-local horizons to substitute event horizons. And the basic notion that we're used is there are marginally trapped surfaces. Technically, the notion I'm introduced is due to Penrose. There's a slightly different notion due to Hawking, just in case you look at the literature and may get a little bit confused. So this is the Penrose's notion of marginally trapped surfaces. And then the quasi-local horizons are supposed to be obtained by stacking the marginally trapped surface on top of each other, so you get a world tube of marginally trapped surfaces. And then the simplest example is that of non-expanding horizons, and that's what we introduced last time. So non-expanding horizon, we call it delta, is a three-dimensional, everything is smooth, null surface, null hypersurface, such that the expansion of its null normal is 0. And last time we spent quite some time about understanding null surfaces because they're a little bit counterintuitive. Because in that, on a space-like surface, the normal is time-like, it is perpendicular clearly, and its projection is 0. On a time-like surface, the normal is space-like, and its projection is 0. But on the null surface, the normal is also null, and therefore it is also tangential to the null surface, and it is normal in the sense that it is perpendicular to every vector which is tangential to the null surface, including itself. So that is the part that is a little bit counterintuitive, and that's what one has to get used to. That's why I did it very slowly last time. And now we want to we looked at some properties last time, and we saw that, well, if this is the case, then for the fact that the expansion is 0, that means that if you have a hypersurface, let's just draw it. This is not a causal diagram, so let me just draw it like that. This is our delta, so this is not a space-time diagram. So this direction is really null direction. And then we look at a cross-section. This cross-section we can call A. And then the statement is that the expansion is 0. That means that the area or the area element of the cross-section is always equal to 0 for every cross-section of this null surface. So that means the total area is actually constant. So the derivative, time derivative of the area, or time derivative of the null time derivative of the area element along the null normal is just 0. So in particular, the area is constant. But we saw that there is an additional facts about this. Just because it's a null surface, therefore, of course, null normal is automatically geodesic. So this is equal to this proportion by NP. So this is the first property we saw. And the second property we saw was that Liel of QAB equal to 0, where QAB is the intrinsic metric, signature 0 plus plus, and this is the pullback of GAB to the manifold. This is a kind of a notation that was introduced by Bob Garrosh, and I think is most obviously, you sort of see it's really being pulled back. You don't have any problems about this. In mathematics literature, just for people who have looked at it before, we're got a full space-time M here. This is a 4-dimensional manifold. And I got a 3-dimensional surface delta up here. And therefore I got an embedding of an M into delta. If you give me a 3-dimensional manifold and there's a 4-dimensional space-time, then of course I got embedding, and every point goes to itself. It's an obvious embedding. So I got here this embedding, delta goes to this pi. And this pullback that I told about in mathematical literature, they'll call it pi star of GAB. So you're pulling back GAB from M to delta, and what you get is QAB. This is just we don't need a pi and so on. So it's understood that this is the pullback. Okay, so this is where we were. Any other questions? No, okay. So what we saw was that this is kind of a notion of equilibrium, one notion of equilibrium. It says that on a non-expanding horizon, the intrinsic metric is time independent. By time we mean motions along this null vector field Penn here. Okay, but in fact, this non-expanding horizons inherit a much richer structure, and that's what I would like to tell. And then, using that structure, we can introduce more useful notions of equilibrium or of time independence. Okay. The next structure that I want to introduce, and I'm again going to do it slowly because not everybody here has sort of looked at differential geometry in this particular way. So the point is that this is a null surface. Now, if I got a space-time and I got a manifold, the full manifold up here, space-time manifold, and on a space-like surface, I get an induced metric which is positive definite. Now, in space-time, we all know that we've got a metric and there's a unique derivative operator which is compatible with it. What people call covariant derivative operator, but since we do everything covariant, and it's a repetition, there's no need to say covariant. I mean, we don't do anything which is not covariant. So okay, so it's a derivative operator, and we just take these derivative operators to be torsion free in general relativity, right? They're just assumed to be torsion free, and therefore the statement is that given the metric G, there's a unique derivative operator grad or nabla, which is compatible with the metric and which is torsion free. Now, if you give me a space-like manifold, then again I got a metric on it which is positive definite, and therefore there is again a unique derivative operator on it which is torsion free. If you give me a time-like manifold, there's a unique derivative operator which is torsion free because I got a metric here which is signature minus invertible metric minus plus plus. But on a null surface, this metric Q is not invertible because I got a degenerate direction up here. As a result, there are infinitely many torsion-free derivative operators. On this manifold delta, compatible with the satisfying So I don't have a unique one, I got infinitely many of them, just because this is not invertible, because it's not invertible. I'm going to make a detour for 1 minute. This is the second part of the lectures. We'll finish black holes hopefully next time. And the second part of the lecture will be on gravitational waves. And in full general relativity, when we want to talk about gravitational waves, we use null infinity scry that I introduced, and we'll talk about it a little bit more next time. But you see, the way that we introduce scry is a null surface. This is with respect to the conformally rescale metric. It is actually a null surface, and it's also divergence free, right? In fact, the null normal n to scry satisfies the grad A and B equal to 0 on scry. Right? So in fact, divergence in particular is 0 of this. So surprisingly or not, it is a fact that scry is a special case of non-expanding horizon, but with respect to the conformally rescale metric, not with respect to physical metric, conformally rescale metric. Here we're talking about conformally physical metric. So in this detour, 2 minute detour, scry can be thought of as a conformally, as a non-expanding horizon with respect to the conformally rescale metric. And therefore it has infinitely many derivative operators, not just one. And the interesting thing is that what you mean by gravitational waves, what you mean by gravitational radiation, is all encoded in the fact that there are infinitely many derivative operators. We will see that there are exactly 2 degrees of freedom in this choice of D. What does that mean? We will see in great detail. There are 2 degrees of freedom on scra in each choice of D, and that they represent precisely the two radiative degrees of freedom of the gravitational field. Quantum mechanics, we can call them gravitons. In the classical literature, you can just call them transverse traceless modes or whatever. So this is therefore also important. So I'm purposely structuring this course in such a way that material we do in the first part can be used in the second part in a seamless way. So that was just a side remark that I put aside now. We're going to come back to it, but so don't forget about this fact. Now we come back to the issue now we're under discussion, which is really expanding, non-expanding horizons and quasi-local horizons to replace the event horizons. And now we're talking only, there's no conformal completion now. There's just the physical metric, and then this Q is degenerate. But we do have a physical metric in space-time. And it turns out that that physical metric and its derivative operator can be pulled back to the non-expanding horizon to give you a derivative operator here. So you get a unique derivative operator here, which is not true on a general null surface. You cannot put it back on a general null surface. But both scra and this the non-expanding horizons that we're going to consider, the black hole horizons, cosmological horizons, they all are very spatial, and for them, the space-time derivative operator can be pulled back to induce derivative operator. So there's a point up here. So now we got the metric of GEB, space-time metric GEB. We got the derivative operator graph, which is torsion-free, and it satisfies grad A of GBC equal to 0. And the statement is that this can be pulled back. So what I would like to do is do this explicitly, but a little bit slowly, because not everybody here is probably familiar with derivative operators and such things. So let me just do it here. And again, because we're going to use it at infinity several times. So what is a derivative operator? Now usually, people say there's a parallel transport and there's a Christoffel symbols and so on, but we're not using coordinates. Our treatment is all manifestly coordinate independent. You can use coordinates anytime you want, but the basic notions don't involve coordinates. So what is a derivative operator? So let me just tell you what it is. So I begin a little detour here about what the derivative operators are, and here I'm just going to consider just a manifold, no metric, and then I will talk about a derivative operator. So a derivative operator, it is grad A. In this abstract index notation of Penn, if you like, grad A is really an operator, as it says up here. It maps tensor fields on manifold to tensor fields on the manifold. And if a tensor field has a structure BC, DE, it is mapped to tensor fields with one additional A. So it has one more index, one more covariant index, and we by convention put it in the first place up here. And this we just define to be equal to grad A of BCE. So it just maps any tensor field of this kind to a tensor field with one additional covariant index, right? Such that, and that's it, right? And we're just going to write down a few properties, and that's what a derivative operator is. So you don't have to check any coordinates, you don't have to check any transformation properties of Christoffel symbols or anything like that. That's it, such that. First, there is a linearity. So if you take grad A of T, BC, DE, plus some constant K times T tilde, BC, DE, then this is what you expect, grad A, T, BC, DE, plus this constant K comes out. Is a constant K times T tilde. It's This is very profound, not very profound, it's obvious. I mean, all the tensorial operations we do are all linear. That is the whole point of the tensor fields up here. The second thing is that it satisfies Leibniz rule. So this is the point that which makes a derivative. Leibniz rule is what always makes a derivative. So Leibniz rule. Philosophical circles say that Leibniz later in his life actually dropped T because he didn't believe in time. It is true that there is a very deep idea about relational time and not absolute time of Newton's. But I'm never sure about it really is true or not. So the statement, Leibniz rule is just this thing, that if you give me T, B, C, D, E, any tensor field, and some other tensor field, let's call it T tilde again, M, N, P, Q, then the derivative operates on this, keeps this constant, then keep this constant, operate on this. So it is just equal to B, C, D, E plus times T tilde and then Q plus B, C, D, E plus. This looks boring, but the important thing is that that's all we need. We don't need anything else. If you want to check if there is derivative operator, that's all you have to check. So got A, T tilde, M. Okay, so that's satisfied. And the third property, which really, at the moment, is all algebraic in a way, right? And we're just saying this operation which does these things. And this is the property which roots it to the manifold and makes it really like a derivative operator. At the moment, it could be, I write it as graph, but it could be an abstract operator from tensor fields to tensor fields, and it has nothing to do with actually what we think of as derivative, nearby, difference between nearby quantities up here. And it says that if you give me a function, grad AF is the one form, satisfied. It adds one more in the index, so of course it's covariant index, so of course the one form, satisfying VA. If you take any vector field VA, grad AF, that is the same as the derivative of V. And this is equal to, in any components if you write, so let me write down components with tilde notation up here. So this is just equal to VA. Here these are just coordinates. And the statement is that it maps. So grad F is a one form such that the contraction with that one form, with any vector field, is just the lead derivative, just the directional derivative. And this can be computed in any chart if you want explicitly. Or those of you know, we just say that grad A of F is just an exterior derivative. That's it. It's a dF. I mean, that's this. Okay. So this is the statement up here. So for all vector fields. That's it. That's a derivative operator. You just check these three things, and then it's a derivative operator. And then everything you know about curvature, Riemann tensor, Ritchie tensor, anything that you want to calculate later on, just follow from these three notions. Algebraic symmetries of the Riemann tensor, anything you want to compute, it just comes from this. There's nothing else. Okay. So this is very useful to have it just in your head that that's all a derivative operator is once and for all. It just removes all kind of junk, right? You get rid of the excess baggage and you just focus on what it is. And the fourth condition is what is a torsion-free derivative operator. So these are the general derivative operators, and then torsion-free. So grad is torsion-free if operating on function, grad A, grad B, F, is symmetric. And we always use torsion-free derivative operator. So that's what general relativity does, so we just always use torsion-free derivative operator. So when I say derivative operator from now on, I just mean a torsion-free derivative operator. I won't say it explicitly every time. So these are the 4 conditions that the derivative operator satisfies. So what is the idea here? We have a non-expanding horizon, which is defined as a submanifold of the full space-time with this structure. It has an intrinsic metric, but it's degenerate. And now we want to know, is there a derivative operator on this manifold? So if you are just put in a room, you know this is what a derivative operator is, this is what a manifold, this is what is given to you, you want a derivative operator. So what are you going to do? Well, what you need to do is the following. You just need to tell me what is dA of a vector operating on some vector field. Let me now call the vector field T. T is tangential to the thing. So now we come back to this original problem after this detour, and then we say that, well, you define a D on a manifold delta. What we need is the following. We need the following. We need to know how this derivative operator D acts on various things. How does it act on functions? Well, it's a derivative operator, so we know how it acts on functions. It is given any function, grad A is that one form, which is defined by this. So if you like, in any coordinate system, the components of grad A are just given by this. So we know how it operates on function. Then the next thing that we need to know is how does it operate on tangent vector fields. So TA, so TB is tangent vector field. So what does it do to the tangent vector field to the delta? If I tell you that, then I'm done. Right? Why am I done if I tell you that? Because if I know the action on the tangent vector field, and I want to know the action on a cotangent vector field, I would like to know what this is. Well, that is very easy, because to know this is the same as saying that I should know what this is for all t. To know this, it suffices to know what this is for all t, because then this tensor field is completely defined up here. But then this, by Leibniz rule, is just equal to dA of dB kB plus kB times dA kB. But you already know what this is. This is a tensor field. If I had told you what this is, I have not told you yet, but why does this suffice? So if I tell you what this is, then you know what this quantity is. Therefore, you know what the contraction of K is with this tensor field, and therefore, and you know what this is. This is just a function, and operating on functions, the derivative operator D is just a gradient. It's just defined by that. So we already know it for functions. Therefore, if you know it on vectors, you know it on covectors. The converse is also true. If you know it on covectors, and you know it on vectors. Now, once you know it on vectors and covectors, then you know it on any tensor. Because if you want to know what is dA of T, B, C, DE is, well, to know this function is the same as just contracting it with tensor fields. So let's call it T, B, T tilde C, and then T double tilde D, triple tilde C, sorry, B, C, D. To know this answer, it suffices to contract with arbitrary vectors, arbitrary covectors on these indices, and arbitrary vectors on these indices, right? But then this quantity on the other hand is just equal to dA of TBC dE times, I bring everything inside, right? And then by Leibniz rule, this quantity would be equal to this minus TBC dE times dA operated on TB BC plus minus TBC dE. Then, so I brought all this inside. By Leibniz rule, this is the same as operating on here. The quantity that I have, all these things outside, plus this out, D operates on this, D operates on this, D operates on this. But every time it operates on a covector or on a vector. And I already know what it actually is on a covector or vector. So tensors are multilinear mappings from vectors and covectors to tensor fields are multilinear mappings from vector fields and covector fields to functions. you know what the derivative operator does on functions. You know, if you know what it does on vectors and covectors, you know what it does on tangents. So times dB dc triple to that. So these are just various covectors and covectors and vectors, and if I know the action on the covectors and vectors, then I know what this action is here.
So we want to pull back the original torsion, the original covariant derivative onto our manifold.
We're not yet done yet, but that's what we're.
This is what we want to do. And your argument is, since we know it has all those things already outside, it will have these features inside. We just want to make sure it's still a function on delta.
Exactly. It's a well-defined operation on that.
Okay, but everything else we already know because it.
Well, I mean, you have to actually show that it. I mean, you're right, but you check that it's true.
Yeah, exactly.
All those things are true, and the statement is that, that because you're completely right. It's just that I don't want to say it's obviously true. It requires 1 minute of thinking, but not 2. So you just do that 1 minute of thinking, and then all the properties of D, these properties of D will follow from the fact that delta graph has these properties on the full manifold, exactly as you say. But what we need to know is what is this quantity. If I have to specify what this quantity is. So if I know what this quantity is, then I will be all done. So first of all, I'm making 2 points. First point is that if I know what this is, then I know what the action on the covector is, and I know what the action on every tensor field is. So the only thing I need to know is what the action on covector field is, or what the action on vector field is. Either way is fine. So we need to know this. Then the statement is that then action on is just determined. This is because we just spread it, if you like, by using these properties. So we kill 2 birds at the same time. One is that we define what is on T, and we define it in such a way that the linearity, the Leibniz rule, are automatically going to be satisfied by T. We don't have to. I mean, that's how we defined it. So therefore, we don't have to check it again. Okay. So then the question is, what is this quantity T? So I mean, obviously, one would say that this is a tensor field. TAB, if you like. So what is this? This is what we want to call. Right? What is TAB? So this should be a tensor field which is intrinsically defined on the manifold. So the idea here is that we want to define TAB equal to TAB. So we don't know what it is, and I'm going to define it to be. And the idea is that you just put it back. So we pull back the derivative operator on T. Now what does this mean? Well, I told you pull back is just a fancy way to say that you restrict the action only on tangent vectors which are tangential. Right? That's what a pullback is. That is to say, it suffices to say, what TAB tilde is, what ought it to be tangent to delta. If I know what this is, then I know what is TAB. There's nothing, So all I need to know is really the pull back just means that, right? So therefore, graph A, B. What does this mean? It means if you give me any vector field which is really tangential to it, then that is just by definition just equal to tilde B grad B of TB. So this derivative operator grad A TB, this B index can be contracted with any vector in the 4 dimensions. But if I pull back, I forbid myself from contracting with arbitrary vector fields in the 4 dimensions. I only allow myself to contract with only the 3-dimensional vector fields. So basically, pull back means lose some information. That's all. Don't allow yourself to contract with arbitrary vector fields. I'll only allow you to contract with the vector fields with the tangent. That's what a pullback is. Okay, so that's what we're going to do. Suffices to say what this is on, And then so this is just the same as this. Therefore, hence, what we're doing is we're just saying that the ATB, or TAB if you like, that is that tensor field which we would like to define this tensor field, DATB tensor field, that when contracted with any T tilde A, sorry, I think that might have been confusing to people. I just meant there are too many B's. So this contraction is just with the in that direction. This I'm not doing anything. So this is just defined to be equal to T tilde A. So we're just saying that D, let's try to do the obvious thing. Namely, that D is a pullback of graph. I know what graph is, so I just put it back. I mean, it's a stupid thing to do. It's nothing very profound, right? I'm just saying, it's a natural thing to do. I shouldn't say stupid. It's a natural thing to do. I know what is graph, and I just restrict the action of graph to I restrict the contraction of graph with the vector fields which are tangential to the free manifold. That's all we're doing. So this idea that we ought to do this. Now, but is this true? Is this good definition? Well, this would be a good definition if TAB. This will be a good idea or good definition, well-defined notion. If this TAB is tangential to delta, right? Because what we want is we want to define this. So we want to, given any vector tangential to delta, we want to define a tensor field which is also tangential to delta. Right? Now this index is tangential by definition, right? Because we are only contracting with tangential vectors. But what about this index? That's not obvious. So the only question that remains is really if this is tangential to delta. Well, of course, the only free index is B here. So the question is whether this tensor field is tangential to delta. But as you all know, a tensor field is tangential to delta, quantum variant tensor field is tangential to delta, if and only if its contraction with L vanishes, because L is a null normal, and therefore, that is to say, if LB so the question is this equal to 0? That is our question. If this were equal to 0, then we are done. So this is a lot of abstract thing, but it really is true. That's how I calculate everything. I don't have to use coordinates, we just use properties, and you can calculate anything you want to calculate just using these properties. So the only question is, if in fact this object up here as I defined, I know what is T and T tilde are tangential tensor field, vector fields, any arbitrary tangential vector fields. I take the covariant derivative of T. In other words, to do this, I take the covariant derivative of T and then I just do this contraction. The question is whether this satisfies LB times this is equal to 0. That's the only question that we have. So let us just do the obvious thing. This is all in space-time now, and therefore I can just raise and lower those indices. So I can write as LB T tilde A TB equal to 0. Actually, I can leave it as it is. Let me leave it as it. I don't have to raise and lower things. Leave it. But now I just graph satisfies Leibniz rule. Therefore, LB T tilde B TB. I just bring this inside, I get T tilde A grade TB and B minus right? I just use Leibniz rule, which of course this derivative operator satisfies. So we just do that. But this quantity up here, on the surface, this is 0. On that. That does not mean that its gradient is 0, because function can be 0, but its the derivative may not be 0. But we are only contracting in the direction of delta. And this quantity is 0 on delta completely. So if I contract in any direction within delta, then of course this is again 0. So the statement is that therefore this is equal to 0 minus T delta A dB grad A LB. Right? That's what we get. And yesterday, when we sketched for you the argument, when we showed that in fact Lie of QAB equal to 0, Lie of QAB was symmetrized derivative up here to where exactly this thing, except that this was symmetrized. Okay. But I told you yesterday that in fact what you can do is, given this manifold up here, given any t, you can write this TA as some alpha times LA plus some vector field HA, which is horizontal. I just decompose it into L part and horizontal part. This is H, this is alpha times LA, this is HA, this is the vector TA. And if you just do this decomposition, and for T tilde TV, you'll get 4 terms up here. And I told you last time that all those 4 terms are 0, just because, first remark, this is equal to 0, and secondly, shear of L is equal to 0, and expansion of L equal to 0. So this is going to be a homework problem. I told you last time, and that's exactly what we have. So here the statement is that this is 0, since LA divided LB is proportional to LB, shear of L equal to 0, and expansion of L. So, because delta is shear free and expansion free, it is true that this quantity is equal to 0. But if this quantity is equal to 0, that just says that indeed the grad A TB pullback is tangential to delta. And therefore, D is the derivative operator. Is a torsion derivative operator. Delta. So, the metric is obtained by QAB is just the pullback of GAB. dA is obtained by saying, in fact, we're just pulling back the derivative operator, the full space-time derivative operator to delta. It's just a pullback, the derivative operator. Now, since we knew that grad A of GBC equal to 0, if I just pull back this equation, that implies grad A of GBC equal to 0, and that is equivalent to saying dA of QBC equal to 0. So the derivative operator, or D, is just the pullback of the full derivative operator. The metric Q is a pullback of the full metric G, and because grad kills G, D kills Q. So D is a torsion-free derivative operator which kills Q. This is what we had hoped, but as I told you before, there are many such derivative operators up here, and we are picking one from full space-time. In case of general relativity, we'll see what happens. In the case of gravitational waves at Scry, what happens is that each space-time will give you one such D, but Scry is sort of the null boundary of all space-times, which are asymptotically flat. So I can change the metric inside. So if I change the metric inside, grad inside changes, of the conformity rescale metric changes, and therefore when I pull back, I get different Ds. These different Ds encode if there is radiation or not. So if I curve space-time and I pull back, I'll get a D. That D will have no radiation. But I have 2 black holes which are rotating, and they coalesce, or they're just rotating if you like, forever. Then they're emitting gravitational waves, and then in that case again I go to space-time.
scry is the same, is the null boundary at infinity. I pull that back, I will get a different D. That D would have motion, would have gravitational radiation. So this fact that you have got different Ds is what really is how the gravitational radiation is encoded in a scry. In our case, because a scry is a universal null boundary, it is not tied necessarily to any one given space-time. You can say that, well, take this scry, use one metric, which can confoundly completes it, and then I get some derivative operator, I take another metric. But here, of course, the horizons are not universal. Right? I can have a star, in which case there is no horizon. I can have a black hole, in which case there is a horizon. So the horizons are not universal, so there is a difference between the two. I hope I don't confuse you too much, but I just wanted you to get a glimpse of this, because when we do gravitational waves, I'm going to do this in much more detail, but at that time then you should be able to see the connections. This connection, by the way, is not well known, but there is such a simple relation between the horizon and null infinity. But this isolated horizon, not event horizon, but isolated. Okay. All right. Or the non-expanding horizon. Okay. So now this is remarkable. I mean, we are using energy condition and Einstein's equation. Right? But once you have done that, then the statement is the following. That we really just ask, look at the definition. So it looks almost, we're not asking too much. It's a null surface such that the expansion vanishes. It looks like just one condition. But that one condition told us that the shear is zero because of Einstein's equation, and the stress energy tensor satisfying the energy condition told us that shear is zero, expansion was already zero. It told us that L is actually geodesic vector field. It told us that dl of QAB equal to 0. It told us that there is a natural derivative operator D on H, or on the horizon, the delta, and which analyzes the metric. So all this structure just came out of this one little thing, right? The one little thing was that this expansion is equal to 0. So we're going to see the same structure as scry in the next part of the lectures. Good. So now the statement is that we got dA on scry, on the non-expanding horizon. Okay. So what non-expanding horizon says, condition says that, well, we got the L is satisfying null geodesics, and this is in equilibrium in the sense that the metric, the intrinsic metric, is actually time independent. But as you know, in general relativity, we got the intrinsic metric, or space-time metric, but we also have derivative operator, we also have curvature tensor, which is obtained by commuting the derivative operators, and all of those things have richer information. Now, in this case, in full space-time, the metric GAB determines the gradient, the derivative operator grad, and the derivative operator determines everything else, right? Determines the curvature tensor. So all the information, the curvature tensor and so on, really comes from the metric. But here, something else is happening. There are infinitely many derivative operators compatible with Q. So dA on delta satisfies, is torsion free and satisfies dA of QDC equal to 0. But from intrinsic structure of delta, D is but one of infinitely many derivative operators satisfying this condition. So if I did not have the full space time and I just say look at a D, which I write as a metric, it doesn't pick this one out. This came because we had the full space time derivative operator, which we pulled back. So there is more information in getting the derivative on delta than getting just the metric on delta. So if I just have the metric on delta, that doesn't give me D, because there are infinitely many of them. Our delta D, which is the pullback of big D up here, has more information. Than the metric. it has some information that is not more information, not determined by the metric. So D is not determined by the metric, there are infinity many, so it has more information. So now it really is up to us to say what we mean by intrinsic geometry, right? At the moment, the natural thing seems to be that, well, I mean, I got the metric, and that's what I mean by intrinsic geometry. But that is our notion usually, because in space-time, if you give me the metric, the derivative operator is also defined, curvature is also defined, etc., etc. But in this case, knowing the metric, the derivative operator is not defined. Derivative operator that we have is an extra structure. So we could say that, well, no, by geometry I mean both the metric and the derivative operator. What do you mean? There is a question that, it's a matter of definition, but that's what we need to understand as to what this intrinsic structure is. So the first thing we note is the following, as an aside, that if I take dA and operate on LB, okay, it's the same identity I'm going to use many, many times. I operate this on LB up here. Then what do I get? Well, this object has a property that if I take any tangent vector field to the axis horizon, so this object is just going to be equal to dA of LBTB and we are introducing I'm just lowering the index using the full space dimension up here. So G8, so this. But this is 0 minus, I'm going to get L. Minus, just 1 second now. Yeah, okay. So note that if I take this quantity, then that is the same as E dot L dot T minus LB. Or maybe I don't even need that actually. Yeah, I don't even need that. So what is this equal to? This is just equal to TB. I can write as TB grad A LB. Okay. So this quantity is the same as this quantity, just to pull back. Maybe I should do it slowly. So I get here TB, and then this is just grad A times LB. Right? That's what the declaration up here is. So that is the same as TB grad B times LB, where I'm just raising and lowering this is up here. And now this is just equal to, we just saw that T tilde A, TB grad A LB equal to 0. From the statement up here, T tilde A, TB grad A LB is equal to 0. And therefore this is equal to 0, therefore this implies that TB grad A LB equal to 0. And therefore, hence, we can prove that TB dB of LB equal to 0. So if I take dALB, then it is always, this index, it is always perpendicular to any vector field which is tangential to the 3 manifold. Therefore, that means that dALB, the only way this can be perpendicular to any 3 vector in the manifold would be that this is actually proportional to LB itself. The only thing which is perpendicular to every vector which is tangential is LB itself. So therefore, this is the form. So, furthermore, we conclude, just with the non-expanding horizon, that we not only have this preferred derivative operator, but this derivative operator on L gives us a 1 form times L. It's again proportional to L. Just like the acceleration was proportional to L, the other derivative, the intrinsic derivative is actually proportional to L. And in fact,
So this intrinsic property are up here. This omega is called, for a reason that will become clear next time, is called a rotation one form. And we'll see that it actually has information about the angular momentum of the horizon, how much horizon is. So dA LB is equal to omega LB, actually is called the rotation. Now, I can take, yeah.
Has there any other derivative operator been studied on these null surfaces that are not expanding, or did everyone always go to this kind of obvious one?
I mean, you can put any derivative operator that is property, but it has no physical meaning. This one has physical meaning because it is induced by the space-time derivative operator.
It's like no one really went into it because it doesn't make sense really.
It makes perfect mathematical sense,
But mathematically,
no
yeah,
physical
physically.
meaning.
So a sense for his question that's sort of interesting, you were telling us that the different derivative operators at Scry carry information about the gravitational radiation reaching Scry. Is there any sense in which that could be generalized to a quasi-global?
No, because the statement in the Scry is really different. Scry is universal, as we'll see.
Yeah.
So the statement is given any asymptotically flat space-time, I got a null free manifold, which is an intrinsic metric and this vector field, perpendicular vector field, and that is common to all. This structure is common to all asymptotically flat space-time. But the horizon structure, the non-expanding horizon structure, is not common to all space-times, and you even admit this horizon. Kerr's space-time has omega, which is not equal to 0. Schwarzschild space-time has omega, which is equal to 0. So therefore the statement is that you could say, and we do often, say that, well, consider a space of all non-expanding horizons. And then on the space of all non-expanding horizon, it is indeed the case that we can do what you want to do, namely just allow all possible derivative operators, which will be induced by some metric, not a given metric. But that is not typically what one physics, in terms of physics studies, because in terms of physics, one is studying about not universal horizons, but one is studying the horizon of a given physical space-time. So you're right, one can consider that, but so in answer to Shorov's question, I said that, well, you can introduce any derivative operator, it doesn't have any physical meaning. I mean, it doesn't have physical meaning in the space-time that you are considering. If you consider.
Yeah. Can I ask one follow-up?
Yeah.
I'm just wondering about ADS or some of these where we don't have a null infinity in the picture. So this picture just is not present in that case. Is
Right.
that?
So in case of ADS, then it really is the case that it's a little bit complicated. But let me just say that in that case, the boundary is time-like.
Yeah.
And then, in order to make the initial value problem well defined, because it's a time-like boundary, so you have to have some reflecting or something, So there's a standard boundary conditions that one puts that I proposed many years ago, which is called now reflective boundary condition, which is really saying that the magnetic part of the y intensity is equal to 0, and that is what. But if you impose that boundary condition, then there are no waves which are going out to infinity, and that is because we are reflecting everything else. So therefore, the statement is that there is no gravitational waves in the standard ADS framework, which are registered which are registered at infinity at Scry. In the sitter, it is a different story, but it's a long story, so I will not go into that. Okay. So is this clear, Shora, what I was saying before? I answered to your question. I was looking at a given space-time, not the space of all space-time. I think, but the point that both of you raised, especially what you just said, what Hal just said, is really important because there is a distinction between Scry and this horizon, even though the structures are very similar. So we can have the cake and eat it too, in the sense that we can exploit the similarity, but keeping track what the differences are. All right. So now we just look at LA grad ALB. We know it's proportional to LB, that's what we are seeing. And now we see that LA grad LB, this of course is the same as LA BALB, because I'm contracting this with something which is tangential to Scry, tangential to the non-expanding horizon, and therefore this is just equal to LA times omega A times LB. So it's just a contraction of this rotation in one form with L, and this is called kappa. and it's called surface gravity. So there's the surface gravity of the horizon, and there's a precise sense in which, but I mean you have to spell it out technically, but in which this is called surface gravity because it is the analog of the little g on the surface of Earth. Right? I mean, what is little g on the surface of the acceleration due to gravity? That acceleration due to gravity in our units as dimension is acceleration is normally length times 2 to the minus 2, but since c is equal to 1, it is just L to the minus 1. And this has dimension of L to the minus 1 because I got a derivative operator operating up here. So this is the acceleration of gravity. And then for Schwarzschild, so Schwarzschild, of course, horizon is in particular non-expanding, and for Schwarzschild, kappa sub L is equal to 1 upon 4L. So it goes inversely as m. No, okay, it goes inversely as that's important to know. And therefore, the acceleration due to gravity actually decreases on the surface of gravity on the surface as we got larger and larger mass up here. Okay. Again, I put g equal to 1, otherwise I should put gf. Okay, so that's called the acceleration. And now you can just check that if I take L prime A to be equal to F times LA, this is just a rescaling, which is a function of delta, then kappa L prime is equal to F times kappa L plus log of F. More generally, if this is the case, then you can check that omega prime is equal to omega A plus dA of log of F.
In what direction is this surface gravity acceleration point? Is it in the direction of L?
It's a scalar. It's like g. It's not a,
Oh, okay.
it's a scalar, like little g, like kappa L is scalar, as you can see. But if you wanted to construct the analog of the vector, then it would be in the direction of L.
Direction of L.
You just write TA double A to the back LB equals to 0, and here TA is an arbitrary tangential vector field on the data, and now you write LA double A LB.
Yeah, very, very good, thank you. So the statement is that here, what we're doing is, good, that's very good. Okay. So LA is tangent to scribe. Very good, okay. LA is tangent to scribe here, and of course not 0. But if I take LA, that is GAB times LB. Okay, that's the point. If I take the pullback of L, pullback of this, so this is QAB times LB, so that is equal to 0. So in fact, I could have, since both of them are actually projected, this really is a pullback, and therefore this would be 0 just by the fact that pullback of L itself is 0. So it would be much more, there's a stronger result I did not go into. So L up vector field is a vector field in space-time, and if I go to scribe, go to the horizon, then it's just tangent to the horizon. But L down, if I lower the index and I get it to scribe, then that's not 0, it's some covariant vector field. But if I put it back, this is equal to 0 because this is a covariant, this is a non-normal, so it is tangential to on delta, it's always equal to tangential to delta. So we want to keep this is very good. I mean, I think the homework you'll see some things of this, but this is very good. That's it. So LA grade LB is equal to that. So this is fine, but dA of LB is actually 0, because if I'm where to lower this index, the only way I know how to lower this index would be by using Q on intrinsically, and that actually is just 0, because LB itself, pullback of LB itself is equal to 0. Okay.
Very good.
This is a delta, not a scry, right? LA is tangent to.
Yes, delta. This, it looks like that. Okay. All right. So now, just a couple of definitions, and then we are finished. So the first definition is about. I know that this last lecture and this lecture was rather mathematical, but we need to do that in order to understand the structure. And now I'm just going to tell you the results and the physics of these results, and then it will be all clear. But I think it's important for you to understand the basic structure which lies. So even though I will not do all the details in the class, any of you who are more mathematically minded and want to do those details, you are really fully equipped to calculate those details and read the paper, or just do it yourself. If you do it yourself, it will take twice as long, but not 8 times as long. So it's okay. All right. So the point. So what I said before was the following. What I'm trying to do is to understand what we mean by a quasi-local horizon in equilibrium. If you just want to say that by horizon we mean that the metric on the horizon doesn't change in time, then non-expanding horizon is good enough. But you may want to mean more things. You may want to mean, for example, that given the quasi-local horizon delta, and we've got the null normal L. I mean, we've got infinitely many null normals because I can rescale L by that. So when I say L, I just mean L equivalent to L times LA. But we've got the metric. The metric does not change. Metric is is universal, does not depend on this rescaling up here. And then we've got this dA. And the dA is also changes, right? I mean, because d, as we just saw, this omega changes basically. So dA LB omega A, where with if I change L, then d will change, namely d will go to d prime. So d prime times L prime will be equal to that. Okay. So then the statement is that this is what we're given up here. So we might want to say that by geometry, I got many possibilities. Geometry, I can mean just the Q and this. Let me call this equivalence class L, and then I can just call it QAB. Okay. This metric Q up here. That's what I mean by geometry. Then the statement is that equilibrium is a non-expanding horizon. But you may mean by geometry, second possibility, is a stronger notion. I got this L and I got this QAB. And we also have this omega up here. And I may say that, well, I got this omega. And I may also ask that L of omega equal to 0. Now this will not be true in general, so this is really an additional condition. So we get this angular momentum potential, and we're saying that angular momentum potential also doesn't change in time. Of course, if you've got a Killing horizon, nothing will depend on time. So we're generalizing the Killing horizon, we're generalizing the horizons in Schwarzschild curve. So here, we're just saying that, well, we don't need a Killing vector field, we don't need global stationarity, we just need something which is just locally this way, and then the statement is that we get additional structure. So this, that is to say, I equip delta with those null normals for which L of omega A equals to 0. So given the null normal L, dA LB is omega L. Therefore, ask that this be equal to 0. That is to say, omega is time independent. So this is a stronger notion of equilibrium. And this notion is called weakly isolated horizons. Non-expanding horizons, and now we got weakly isolated horizons. Now it turns out that for every application, for example, application to the laws of black hole mechanics, application in quantum gravity that people have done, They are not use isolated horizons. They are just use this weakly isolated horizon. Namely, we are assuming that Q is time independent and omega is time independent. So this going from the non-expanding horizon to the weakly isolated horizon is just a restriction on the family of null normals. Basically, this function f that we have got here can depend on v theta phi, where v is running this way. So is the affine parameter is like time, affine parameter of L, and theta and phi are running this way. And the statement is that you can use the freedom in f, use it effectively to just always find a null normal such that L of omega equal to 0. So just as a restriction to the family of null normals, and then the restricted freedom would just be LA goes to f times LA, where f is a function only of theta and phi. We don't have further freedom up here. So it's just really like a gauge fixing. You can always do this. And this is important because all the laws of black hole mechanics that people proved for stationary spacetimes, you don't need stationarity. All you need is these weakly isolated horizons. And then they're actually valid. Also, in one stroke, you can have cosmological horizons and black hole horizons. And finally, there's the notion of isolated horizons. So now what we have is really a non-expanding horizon, delta. So we have our QAB, but now restrict L further. Such that the full derivative operator, D that we got up here, is time independent. Such that dl of D minus d of LA, the lead derivative is equal to 0, or this operating on any vector field TA, TP, equal to 0 for all tangent vectors. Now, the only reason we introduced these isolated horizons is because in numerical relativity, the horizons you find always satisfy this stronger condition. So we thought, well, why not just use it? And of course, if you have stronger condition, we can do a little bit more things with it. That's why we. But from a theoretical perspective, that is to say, from a more mathematical physics or quantum gravity perspective, or laws of black hole mechanics perspective, it suffices to have just this. So let me summarize, and then we can stop, and if those who have questions can stay. So the statement is that we are almost done with the quasi-local horizon, kind of the foundations, and then next time we'll study the properties. The first point is that we have the notion of marginally trapped surface, and then we are looking at the horizons which actually are obtained by stacking these marginally trapped surfaces, such that the three-dimensional surface is in equilibrium. That is to say, some structure on the three-dimensional horizon is time independent. If you have a Killing vector field, then of course, full four-dimensional metric is time independent. Therefore, any quantity which you can construct from the four-dimensional metric is going to be time independent. So for Killing horizon, anything you can do. You can take curvature, you can take fifth derivative of the curvature, they're all going to be time independent. And the key observation here is that we don't need that for almost all applications. All we need is a tiny little portion of the Killing condition. Not everything has to be time independent. First of all, we would like the intrinsic metric to be time independent. Secondly, if on a non-expanding horizon, then the statement, and this is achieved on a non-expanding horizon, and on a non-expanding horizon free of charge, we have a derivative operator which is induced by the space-time derivative operator. This is possible only because the shear and the expansion are both 0 on the non-expanding horizon. On the general null surface, this will not be the case. And then finally, the statement is that we can define the notion of equilibrium a little bit stronger by saying that not only should the metric be time independent, but the piece of the derivative operator, which is selected, which is encoded in this omega,
that should be time independent. So what we are saying up here is that is dA of LB is equal to omega A LB, and we are asking that dL of dA of LB equal to 0. Because if I take dL of this, I get dL of omega times L, and dL of L. dL of L is just 0, so therefore dL of omega should be equal to 0. That's what we are asking. This is weakly isolated horizon condition. And then the isolated horizon condition says that not only should dL of D should be equal to 0, but maybe I should write it. I can write this also as dL of dA minus dA of dL greater than LA equal to 0. This is free because dL of L is 0, so this matter. So on a weakly isolated horizon, we are just asking that that LL commute only with the action of D on L. Here, on an isolated horizon, we are asking that the full dA commute with L, that is to say the action of dA on any tangential vector field should commute with LL. That should be time independent. So this is saying that the full derivative operator be time independent. This is saying that the action of the derivative operator on L be time independent. Now this looks like splitting hair, and I was not happy with it when it happened 15 years ago. I thought it should be something, since that we should just have one definition which works everywhere. But then I really think that it is better to distinguish, because this is the only thing we need for the laws of black hole mechanics, entropy calculations, etc., etc. Whereas this is something that happens to be true in numerical relativity, and therefore we often use it because we can prove some slightly stronger theorems with it. Okay, so I think next week we'll be really done with black holes. It has taken 3 lectures longer than I thought, but I think we'll cut short. I'll ask you, please think about it. What should we do? Shall we cut short a little bit the gravitational waves part, or shall we cut short a little bit the cosmology part? So please think about it, and next time we can have some. Send me an email if you have strong feelings one way or the other, and I will arrange the course accordingly.